Hello, and welcome back to Old School Coding, where I'm apparently live. That was a bit of a delay. Welcome to Old School Coding, where I'm using the techniques of the early 90s and the language of the early 90s to write a simulator for a microcomputer of the early 90s. Let's swing right into it. The bulk of our instructions that are remaining are dealing with reading and writing memory. And currently we have a decoder which is shifting a ROM into shadow at 0, but we have no way in and out of that. We have an explicit call to take us in and out of that, but isn't really well defined. And there's two ways to deal with that. One is to have the memory board itself signal when it's time to come in and out. The other one is to have a I/O device that you can hit that says an output to this port will release the shadow. And I'm going to use the latter. So one of our 255 ports is going to be some kind of a control for the simulator. And we're going to say if we output a specific value to that port, then we will release shadow. And anything else we output will do nothing. Yet. And we'll work out what port that is as we need to. That'll be something that will be set based on what system we're simulating and so on and so on and so on. But to make that work, I need to have the device output instruction out. So I'm going to do in and out. Okay. And the other thing that we need to do, we've got some ALU operations which operate on the accumulator and a immediate operand. I probably should have done them before, so they're kind of in the queue. I'll probably get those done before I start doing these operations on memory, and then stack operations and calls and so on. But today is in and out. So down into ink. First of all, 8080, is there anything in the 8080 that I need to do to support in and out? Well, I don't think so. Because we're going to get the port number as an immediate operand of the instruction. The 8080 does not allow you to take the port number for a register, alas. And that will go out on the address bus. So we don't have a place that we're storing that. It's actually going to go in the incrementer decrementer address latch, because that's the block in the 8080 that drives the address bus. When the data comes in, it's going to be pulled into the accumulator, so we're good there. I do not believe we have much that we need to do. Let's take a look at the instruction itself. Where did my PDF go? There it is. So in and out are second sheet here down at the bottom. So there's a M1T4 that essentially does nothing, and that'll be setting us up for the M2, which is really just a 2 bops setup, kind of like the other guys that need a second byte. And the difference is that when the incoming data arrives here in M2T3, we gain control back, and we're going to take that second byte and we're going to put it in the Z and W registers. So WZ is going to have 0 in W, and it's going to have the IO port number in Z. And then 3 bops, it's not really 3 bops because it's not PC out. Remember, 3 bops is third byte of the opcode, but we'll make something that looks like 3 bops. And actually, WZ out, data to A, WZ out, A to data. I think this is a unique machine code cycle. Oh, right, because the status is IO read and IO write. So the status words are unique for these instructions. So these will be unique. So we 2 bops floating into us. So that's what we need to build. Let us move that off to the side and turn it off in OBS. Nothing really fancy. I believe we have a M3. We do not have an M3 T1, but we will be directing to it from M2 T3, which is ours. So M2 T3 will point at us, and then we can point from our T3 at the proper M3 T1 cycle. So we're good. So I need to have an IO. I8080 underscore IO.c. I'm just going to grab InkDeck as my template. IO to do write good comments. I actually haven't had a whole lot of time off stream to just go over and write new comments. I did have an aborted stream earlier today where I spent an hour messing around with the decoder, thinking that I could have it automatically shadow things in and out, but in the process, it violated one of the design constraints that I set up early on, which was that the clients of the decoder can change the subscription. So the decoder has a whole bunch of places to store, slots to store decoder edges, which should come and go without notification to decoder. But to implement the shadow inside the decoder efficiently, I was trying to have it rewrite the assignments based on shadow, and that would conflict with anybody else trying to rewrite the assignments, so that was a bad thing. Anyway, so I wasted an hour on that instead of writing comments. I'll get back to writing comments. So I8080 underscore IO. Let's get rid of all of this. So IO init. Well, what are we going to be doing here? We need to set up a M1T4 op in and op out. Hold on, let's leave that there for the moment. F8080 state, I believe it was. That's what I get for deleting the stuff too quickly. Let's pull it up in the other window here, InkDeck. Yep, F8080 state, and then the name of the function, which is I8080 IO in M1T4. And the parameters to that are given elsewhere. There we go. This just becomes a big old template for what we're doing here. I8080 IO in M1T4 of that. Now, really, I think I can just use this 2-bops here, can't I? Yes, I can. So this is CPU arrow state 2-bops. So these are really M2 T3s is where I first get control. So M1 T4, we do nothing during the T4, and we deliver control to 2 bops for the second byte of the opcode. That will go down through here. We'll do the normal thing. We're doing a memory read. We're using PC. We're incrementing PC. We're storing it back. And we eventually get control of our M2 T3, where we need to assure that the wait signal has been made low. And here, we are going to be capturing the data from the data bus. So data to CPU arrow Z is equal to, so WZ are the registers of a writing. Z is the most significant byte. W is least significant, so that gets CPU, arrow, data, value. I believe we are responsible for edge low of CPU dBn. Let's check the move immediates. Here. So indeed, we're responsible for setting wait. We'll eventually be setting red M1 int, but not in this guy. But let's copy paste that now. We're bringing wait low. Red M1 int will happen eventually. Data value gets put into a register. We load dbn, and we're asked to deassert the address. Then on this, we need to deliver ourselves to ION M3T1. And the only difference between in and out is where we deliver at the end. Like that. So all of these guys are not used. That. Now let's take a look at our compile logs. Okay. Implicit declaration of edge Z. We don't have an edge Z, we have an address Z. Adder is not an edge. Okay, and we need to declare these guys. And now I can start zapping all of this crap. I did pick a rather large file to duplicate. So there's that. M3T1. So M3T1 is going to be issuing our cycle that actually does the I/O port stuff. So let's start by looking at I8080 underscore, well, it can be like 2 bops, but it's going to be a different status value. So here's a typical T1 here. Now the adder is going to be Z in the upper. It says WZ out. I'm not sure which one is which. Well, let's take a look at the block diagram and reason it out based on how that's drawn. PDF up. So this shows W as being the most significant byte. There we go. So now during here, ION T1, the address is going to be W value left shifted by 8 or CPU Z value. So this code is already set up to allow the full use of W and Z for the IO port addresses. Adder gets the IDAL value, and this is not status mread anymore. This is status input RD and sync. And it will direct us to this guy, M3T2. Now we have the out variant, which is just the same as int, as in, like that. And it goes to status output WR. Otherwise, it's the same. So M3T2, status next is going to be M3T3. Back to 2 bops, look at a typical T2 cycle. So during M3T2, really? Oh, this is Ink PC. We do not do this. So M3T2, we high impedance the data bus so that we can get our data from the device. We turn off the sync, we issue data bus in, and we allow for wait states here. And I think literally that this is shared. If we're willing to go through M2T3. Let's not share it so we don't have to go through M2T3. Yes, this is duplicating a lot of code. It's duplicating it to prevent us from doing another dive through memory, which costs us some time. Am I over-optimizing? Very probably. In fact, let's do just the input path first. In fact, I'm going to just zap the output stuff for now. We'll do in, and then we'll do out. Because every one of these is duplicated the input and then edited a bit. So M2T3, we get the data, and form the address. M3T1 is status input read with the correct address, and the data is there. And then M3 second T state, we hit data bus input. We're going to do the TW cycle here. TW is very much the same, but we get a rise on wait here. So we issue another rising edge of dB in. So the output doesn't have wait states. Devices are expected, I guess, anytime you do a write, the guy on the other end is expected to latch the data and release control. So I don't know what's going on with that. I don't recall. I've been coding behind the PDF. Frick. Well, as long as we got the PDF up, do we see any examples of the wait states being used during write cycles? Input instruction, output instruction. Output instruction C, it says wait is low. Interrupt timing, hold operation, halt, reset. Okay, I am fairly certain that when you're writing to a slow device or a slow memory, you can't simply go boom, 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 right. It would presume, I mean, if I am writing to a slow device, I do an output, I do another output, it's up to the device. If I do a write to a slow memory, where's the memory? Is it ready? Because we aren't actually asserting. Wow. Okay. So, yeah, I guess in our simulation, we are not going to allow wait states on writes. Yikes. Because the decoder isn't going to be sending control to the other end until the write signal goes, and that doesn't happen until later. Anyway, let's concentrate on the I/O read. So here, data bus is ready to receive. We turn off sync, we turn on dB in, we vector to based on the ready value here. And we may have a wait, edge high wait. We reassert the data bus in as high. We check ready again. M3 T3 comes in, and a typical T3 is going to be after 2 bops. We go to I8080 MVI for that. T3, make sure wait is low. Now M3 T3, if we look at the input instruction, I still have the PDF up. I keep forgetting to take down the PDF. So this is going to be the end of the instruction, where we take the input data and put it in the accumulator. We can turn that off, and now we can look at this. Quick overview here. For the input instruction, we are going to use 2 bops to manage the second byte, and it's going to turn control over to us in the third T state of that, where we release wait, capture the immediate, turn it into an address, release dB in an adder, and follow up with the next machine cycle, which is put our I/O port out on the address bus and say it's input read, and turn control over to here, where we do a release the data bus, release sync, turn on dB in, which gets the data coming in, and we check ready. We hold in the wait state until we're ready to go, and we come out of that, we release wait, we I haven't customized this yet. We do release weight. Now, this is the final cycle of the instruction, so we're going to grab this guy. We're going to say, oh, red M1 int. So internal return to M1 state on the next machine cycle, or the next T state. And what do we want to do here? Well, we need to grab the data, same really as here, during phi 2 rising. We're going to grab the data and shove it in the accumulator, release DB in, and release the address bus. And that handles the input. IO in M3T2. And M3T3. And M3T wait. So supposedly now we have the ability to do input instructions. Let's add outputs. Output looks like input. Output does not have wait states. Okay, so out T, let's check that back. Query replace regex word in becomes out. There. So we do the same thing here. We capture our address and we send it out. This is output WR. And we phase down to here, and we do not have a T wait. We do not do a DB in. We are doing an output operation. This may be our first memory write. I think this is our first write transaction from the processor. So let us bring up the diagram. There's the PDF. Drag it in my face so I remember to take it off the OBS when I'm done. So the output instruction cycle, we look at this, we've got a normal instruction fetch where we've got the instruction coming in here at a T4. And then during T5, we get a sync pulse with the status 2. This is the memory read for the second byte of the operation. DB in, and there's byte 2. Notice byte 2, it says this data, when this is low, becomes the IO device number, and we're doing that. And then during the M3, we do another sync, which gets us the status 7. The IO device number is on the address bus, and here we get the data here. And WR is going low apparently during phase 1 of the clock. What does my WR timing look like? I know I tested this. Well, let's take a look. I have some diagrams that I can peek at. PDF go away. So the 8228 has the diagrams, but they're not at all linked to time because it's just combinatorial logic. But if we go down through here, we look for the IO output WR. It's this top one. This says the status strobe has 1-0, and later we get a write signal going low with IOW going low. So the right signal drives IOW. That's all the 8228 knows. And here, the 8224 doesn't know anything at all about this. So this is actually timing we haven't decided on anywhere yet. Interesting. Let's look at the timing diagrams then. So let's see. I believe it's phi 1 falling that gates this. No, it would be phi 1 rising, I guess. I'm just guessing. We do show it happening very early in the T state, but again, this is not a diagram that carries specific timing information. It does just say that WR is low while the device number and accumulator are present. And it's holding all the way out here until the beginning of this guy.
Yeah, 2 water.
So we'll think about that. I may want to narrow that right pulse.
Thank you, Aaron.
Let's see, is there a memory right diagram that I can refer to see if memory right shows us anything else? Interrupt timing. So interrupt timing is going to be pushing some stuff onto the stack. It shows the same vague, early in the T state we're manipulating it. Hold operation, halt, reset. Okay, so we need to scan all the way forward to the data sheet for the 8080. And here's where we determine the actual timing for the right signal. Scan over here, we find the falling edge of right is TDC, timing is TDC after the rising edge of phi 1. TDC says up to 120 nanoseconds, so we should be gating this on the rising edge of phi 1. And on the rising edge of phi 1, we go back up to high again. Oh boy. I am tempted to release right on the rising edge of phi 2 so that we don't have to do it on every rising edge of phi 1. We just do it on the rising edge of phi 2 in the right cycle. So we will be narrowing our phi 2. So as long as I'm doing that, I'm going to narrow down the right pulse so that it is just during phi 2. I am violating the timing of the 8080 on this, but I don't believe I am violating it too badly. This TDC does say we have 120 nanoseconds, and the distance between phi 1 rising to phi 2 rising is 111 nanoseconds. So we are within timing constraints to do this here. However, we are violating the timing on the release because we are doing it before this rising edge. But that's what we're doing. So M2T3. IO out M3. We don't have a T wait here, so we can get rid of this. Edge, low, CPU. Okay. We need to make sure that our data is on the data bus before we send the right low. We are holding the address all the way out through the end of the pulse. Now, I was going to defer this to here. And in fact, I can data to it here. So phi 2 rise, when the sync pulse goes away, we're going to send our data from the accumulator out to the bus. And we are going to hit the right pulse during MTT3. So the right pulse is starting late and ending early. We should be okay with that. And that gives us a chance to release the address bus here. M3T2 does not mess with DBN at all. So if I wanted, if I were redesigning this system from scratch, I might advance my write pulse to start even sooner. Okay? But I'm not. So M3T2, rising phi 2, we get the address and the data, they're out there, and then the next T state, we hit the write pulse, and we're done. Let's check the timing on that. I'm wondering, T2 or T3? Let's make sure that this is, I'm pretty sure the write pulse is during the T3. Let's double check. WR is in T3. Okay, so yes, so it is during T3. So yeah, I will relent a little bit on timing. I'll start it at the right time, but I am going to end it a little bit early. The alternative is that every M1 T1 handler has to assure that it's releasing WR at the beginning of the cycle. Or the clock phase handler for that has to release it when T1 rises, no matter what, always. That's extra work during every machine cycle. Don't want that.
Yeah, I'm right here.
So this means we now have in and out. So for our test mechanism, I'm going to have a port where whatever you output to that port,
I'm sorry,
you get back when you read it in. I'll use 2 different port numbers. But this is all the I/O
I was
test.
making sure I was getting my little bugs and cookies.
So what is this going to look like? Let's write the assembly code first. Notice I've got some more bits of assembly code that are building up here slowly but surely. We've got jump test, which is our test for jump. Call this iotest.asm. Test for in and out instructions. So when we run this test, we know that our conditional jumps are working. So we can use the same RST0, RST1, RST2 dodge to capture errors here. So I am going to move immediate A1 out. I will send that out to port, how about port 0? In from port 255, and then we are going to decrement A, and then DCR does not set the 0 flag, does it? Hold on, let's make sure. And I'm coding behind the PDF again. I'm sorry. DCR, all condition flags except carry. So I set it to 1. Now DCR, now I can say JZ to IO pass 1. RST zeros fail. I'll just call it pass 1. Up. And then RST2 for next subset. I'm going to run a different data value through the same path just to make sure that we're not always reading it. I want to have this be
That's fine. I just
jump on positive,
I already knew, and I was trying to figure out who was who.
and I'm going to send the value 80H. And this is going to come down here, and I'm going to do a done, which is an RST1. Simple little program. So we start with it 1. We decrement it so we know, between here, let's do it MVI A 128. That way we know we're not just outputting from A and then getting the same value back. Now we should see in LST, we should now see iotest.lst, so there's our test program. And let me turn off the PDF. I am so sorry, I keep doing that. So now you can see our test program in the upper right. Sorry. In the upper left is the assembled version. So we start at the top, set A to 1, and send it out port 0. Set it to 128 so we can verify that we're getting something when we do the in255. So the test jig is going to have to say whatever we output to port 0, we can read in from port 255. In fact, let's make these something different. So 55 and 205. Because all zeros and all ones might be misconstrued. In fact, yeah, 55 decimal. So we see this over here, so it's 37 hex and CD hex. So those aren't patterns that we would normally just see from Greg saying, well, if the bus is unknown or high impedance, we'll use a value, and I would not normally use those. I might choose 0 or FF or 55 or AA or something like that. So there's that. So we write 1. We make the accumulator something different. We read the value in, we decrement it, and we pass. Wouldn't it be cool if the port we sent it to actually modified the data somewhat? Yeah, it would be kind of cool, but it wouldn't help the test. JD pass-throughs. There is our test. So test I8080 IO.test. So we're going to look kind of like jump test.
It only gets 12 tracks.
So IO post, we don't have anything yet. I8080 underscore IO underscore test. Let's see.
I'm referring to remembering words.
Okay. Okay, so we can get rid of a bunch of the debugging stuff. The test done and test page, pass fail page, these are all, oh, I do need those, right. So what are we doing here in IOBIST? Setting the accumulator to high impedance so that it will start out with no data showing on the plot. Insert word 0, we're going to save RST012. This is the mechanism we're doing for the subtest. If I start doing this in a lot of places, I will push it on up to a support function. Test done, test page, page number is 0. We are reading in hex / iotest.asm.hex. And we don't need this IO read thing. This is jump read. It was disclosing our jump address for us during debugging. Okay, so here's our standard loop. Clock run 1, handle paging, terminate when we're done, and all of that, and restore. Okay. So this actually, this is looking more and more like we have a standard test program runner, which can take any test program that uses RST012 to do this stuff and run it. This really didn't change much. If we get a third instance of this, I'll start thinking about taking the whole idea and make it just a bit of code that runs a test program where all you do is you feed in what the test program is and it does the right thing. So that's IO test. So now we get to test i8080 test.c. And where we have jump, I'm going to duplicate it and call it IO, and then I'm going to push my cursor there and end that. And now we can go down like that. And put in reset for testing. Oh, come on. So now we have the errors. These guys weren't declared. So inc i80 impl, and we have okay, so the keyboard macro I used was not correct. It happened to work, but it replaced the wrong word. Search for jump. Duplicate the line, search for jump again, replace it with IO, next line. There we go. So now we're getting down here and it says CPU is in phase 1, PC is 3, IR is D3, so D3 didn't get defined. So live coding, source, i8080 io.c, M1T3, M1T4, M2T4. So IO init isn't getting called, I'll bet. Indeed. So IO test fail hit at PC 0x000C. So what instruction is this? This is in IO test here. Okay, so that's failing because we have not yet implemented the thing that captures the output from port 255 in a place where it can be read by the input from 205. We're getting there. So here's our test. So before we can actually start these things, we need to have a function to accept our output and a function to set our to provide the input. And it needs to look a lot like a memory thing. So what do we have? We have a RAM thingy here. And there's not a whole lot of work. So this is just like that. RAM 8107x8x4 is our test dev. Actually, let's, I will just use test dev. So type def, struct, test dev. So we've got a test device. And this is what we're getting when we're reading from it. So we're going to do dev arrow value. And here we're going to say dev arrow value is equal to data values. So we do need to have, dev needs to know about its data here, and that needs to know about the actual cell that it's storing. So we need to say byte value. Now I could be more clever than this. I could be much more clever than this. I could set up value as a data value. So in theory, we could now include this in plots. And not a bad idea. So it's just data of dev arrow value. I'll call that reg. So we have a device that has a CSTR name. We're going to give it a name. This is looking more and more like a real thing now. So that's good because we want to be able to test with something that looks like a real thing. So we have a test device that has a name. It's got an internal register we are setting and reading, and it's got a connection to the data bus. And it also is going to need an edge RD and an edge WR. So it's got internal storage. It has read and write pins. It has data. Let's put the data at the top. Connect to the data bus. It has read and write edges. It has a place it stores things. We have methods for doing that. And just for funsies, static, void, test div init. Dev arrow name equals name edge init of our dev arrow RD is format. And data init dev arrow reg. Too few arguments to edge init because we want to initialize that to 1. Read and write are 1. Assert dev. And I am going to have an initial value here. Data init does not take an initial value. Forget it. So for the write, this is dev data value here.
I can't answer that.
We call into linked. We are going to do an edge.
Going to DE in 3, 2, 1. If you have something that's soft preserved down at the bottom and I miss it, please let me know. Is that Masa? Masa had that? Okay, yeah. Congrats, Masa. And we have a Warrior Rogue Priest Mage token. Warriors, Rogues, Priest Mages. Who needs it? Well, Bone Dry needs it slightly more than Grotesque. Oh, but Nuka's bringing in the 51. So going to Nuka in 3, 2, 1.
We have a test dev called TD.
We ain't checking the rep. It's just how much you got tank space to hold the crap, please. Please stay off the raised area. Stay on the ground level for this gauntlet.
WR defined and not used because I failed to do this. Thought I brought that. Okay, we've got it initialized, we just haven't hooked it up yet. The other thing is, I don't think I did all of the inits I was supposed to do, did I? Oh, TS has all of those inits set up. So what I want to do is test dev init. I want to hook up dev for this test, and then I want to unhook it when I am done. And am I doing anything with ROM here? I am loading into ROM. Good. So deck arrow here, dev underscore RD of the read port. Which I really ought to have set up on an EQU. Let's do that. ASM IO test. TDRP is read port. EQU 205. TDWP QU 55. There we go.
Oh no, clock's dead. We need a warrior to pick up the boss, please. Thank you, Glenn.
Okay, so we ran without reporting anything, which is a good sign because we should be silent, but we want to look at it. So doc, image, we have two IO plots. and they may or may not have been updated during this run, so I'm going to X them out. In fact, I am going to modify this, say RM slash doc image I8080 underscore IO star PNG.
Do we need to mark one on this one?
So there's our first section. IO test. Actually, let's look at the LST file instead. It's easier to read. So first section here. We get the PC 0, 1, 2, 3, 4, and so on. If I can look over this real quick, 0, 1, here's 6 pulses coming in. We're showing quite a lot of instructions here. The interesting thing, we can skip down to the bottom, and we can see this is that IOW is pulsing here, and we can see that we did not add our device to the plot. But we do see that W is set to 0 here, slightly before it pulses, and 37. So we're writing to port 37, and that is correct. And the data bus has a confusing series of bytes, but I believe this is lining up with the 0, 1 value, which is correct. And the accumulator is eventually set to 80 here. And then it is read, and it gets back a 1. There we go. So that's working.
Thank you, Bruce.
And we look at the second one, and the pattern is pretty much the same addresses, and the data we get, this is an 80 goes out, and an 80 comes back, and we see the accumulator. Haha, yeah, sending out an 80 and then changing it to 128 to be different is not going to do that, so I will set that to 222. Just so we get a different value. And I do need to refresh that. Really? I don't think this actually... Oh, I changed it in the LST file, didn't I? Helps if you change it in the source. Change it to 42. There we go. There we go. So we'll set it to 80 and send it out. We set it to 2A, which is 42. And we do the input, and we get back an 80, decrement to 7F, and we get the proper branch. So this is now working. And the last thing I want to do is I want to add my device to the actual plot test. So IO test. And I need to add a trace. So let's take a look at trace. Let's use trace data as our model.
Okay, just leave him alone, he'll come back to us.
And this happens inside BIST. So we're going to do it down here for the moment. We do need to do a sig plot sig on SP. Okay. We do need to do it in init data, which requires SS. Do we have SS? We do have SS. Call this trace TD because it's a TD device register. Okay, so we are initializing our trace TD where? Here. SS, and this requires a data type signal. Well, T data is the dev arrow reg. Plot sig. Trace data, we need to do a sig trace fini. I'm going to put my sig plot sig before that, my sig plot sigs before that, and my sig plot trace fini before that. Oops, I have it. This may put us at the top. I want to put it at the bottom. Segmentation fault. Whee! So F put C way down there.
Agility, stamina.
Let's get out of the library code up into sig trace. So we are trying to
DE,
fprintf onto the file pointer.
2, 1. Yeah, I'll get to those in a second.
So I'm thinking that our sig trace didn't get properly initialized. So there's sig trace TD.
Need a book.
Sig trace init data, trace TD.
Going to Anna.
Sig trace init. It should
And
be.
we have a Drake token for Paladin, Hunter, Shaman.
So there's where we opened the file. Ah, there it is. Well, we're doing a sig plot fini. Okay. We do not want to do a sig trace fini until we are actually done down here.
The last piece of.
We're doing sig trace fini several times. That's not good.
Give me a roll for those.
That is much better. And now you notice at the bottom we have this TD reg thing. So we look at the first plot, we see that the test device register is Z state, and then it becomes 1. And then it changes to 2, it changes to 80 here. So we are now properly doing input and output to an I/O device. Yay, and that only took us an hour. So I am going to commit this to Git, and then we're going to start working on the next bit of code. Let's bring up Git Kraken. Few changes.
We do have a couple.
So there we have the test program staged up. The implementation, we're adding IO, init, and so on. I'm just going to say add the submodule that covers a whole bunch of these bits of boilerplate. io.c, this is the new file that implements it. Under 200 lines, that's good. People that think that each source file needs to fit on one screen can bite me. Or they can buy me a screen that can hold 500 lines. One or the other, I don't care which. IO test is very much like jump test. I will not put that in the Git comment. We will talk about those being similar in the future if we unify it, which we may. So we'll add those and push it up because it's working and the test is complete. So we now have this IO port capability that we can use. So in theory, our boot ROM could use a IO port to get us out of memory. So we're going to, I'm going to make a note of that really quick here. So i8080 bootrom.asm is where I'm going to put my boot ROM stuff. So it starts at 2 kilobytes from the end of memory. Boot ROM lives in the top 2K of memory during shadow. Top 2K of memory. During shadow also serves memory reads in the bottom 2K. Because we are not messing with shadow. I started messing with shadow earlier and it took me into an hour's worth of work ending up in, oh, but you're violating a design constraint on the decoder, so we're not doing that. So what we're doing here is we are going to jump up into the ROM. In fact, I think I'm going to disable interrupts immediately and then jump to .+3 and then set up our stack pointer, which is going to be below the disk buffer. We need to figure out a good place to put our stack pointer. We really do. In fact, I'm not going to do that. So we're going to jump to, I'll call this 0. Jump high. So high is where we're going to enter the ROM itself. And we're going to have a EQU up here. So C port, so our control port, EQU. I'll put on 254. I think 255 is used by MDS. Well, we could put this on 255. Simulation control port. I may have a control input port and it may not be on the same number.
Mouse of the boss is on you. Be careful.
Returns 8 simulation status bits TBD. So I'm going to define that we have a CI port and that does return 8 bits of information, and I'm not going to say what those 8 bits are. Actually returns status code TBD. So it's going to return some sort of byte that does something. We'll work it out when we get there. So hi, we're going to say MVI A comma 0. Actually, we're going to say XRA A to get a 0 in the accumulator, and we're going to say out coport halt. So here is our boot ROM so far. We disable interrupts, jump high,
Might want to take him up the
out
hill
that.
a little
And
bit.
actually,
Don't
I'm
go
going
too
to
far.
EI
You have
halt.
to jump down and you don't want to die.
So in theory, this will leave
And
us
don't run
halted
into
with
deep
interrupts
water.
enabled. And our devices could then interrupt us and give us a jump instruction, and we would go do that. It would return from the jump instruction, and it would come back to after the halt. So after halt comes back, I want to jump high. I want to jump back to here. I will call this idle. This is now an idle loop where we assure that our no, idle loop is just this. So 0 is entry point used at reset when shadow maps this ROM to memory reads at
Clean up bag. Oh, good. Folklore, your sacrifice will be rewarded. Yeah, but you didn't self-preserve them. Congrats, Folklore. We got a warrior book.
So there is literally the simplest operating system in the world. With a front panel that allows you to read and write memory, to reset the CPU, or to issue a start at this address. And start at this address would be interrupt request, followed by a jump instruction and the 2-byte address. That gives you a way from the front panel to toggle in a program and to run it, and to have the blinking lights go, and at the end of the program, it does the right thing. So I think that what I'm going to do is when I get to high memory, actually at idle, what I'm going to do here is I'm going to LXI SP how about this? ROM mem top EQU OF80H. Let's say this is a 32 kilobyte memory, 48 kilobyte memory system, where the ROM sits in the top 2K of the actual address space. There we go. So we're going to have a, I'm hypothesizing a system where we have this big hole in the address space where any access into that hole will just dump us into an infinite wait. This involves having the decode manipulate weight, and we'll worry about that later.
Need the big venom sacks.
I am good with this. We've
Yeah,
got
that's what
our
I
ports,
understand.
we've got memory size, compute the top of memory. We have entry point at reset where we disable interrupts and jump high. We may do some more things here to initialize the system with interrupts disabled. I think there is a 1 cycle window here coming out of reset where interrupts might be. No, because interrupts are sampled when M1, when the return to M1 thingy is high. So if our first instruction is disable interrupts, we shouldn't be taking an interrupt ever. Then jump to high, get to high memory. Potentially we have machine initialization here before we enable interrupts. So for now, that's just turn off the shadow. We get into idle. I'm going to reinitialize our stack pointer to the top of memory, enable interrupts and halt. And if we come out of halt, say because we did a interrupt, we're going to jump back to idle where we reset our stack pointer to the top and continue. This is just in case, well, if we're returning from an interrupt we get here, it means stack pointer is probably okay, but this is not a bad thing to do. We could also initialize anything else here that we wanted to set up. Now, from when you take an interrupt, it's going to disable interrupts, and typically at the end of an interrupt handler, you enable interrupts in return. So theory is when we get back from the interrupt here, interrupts should be enabled. Yeah, let's not mess with the stack pointer here. Let's do that here. So we get to high memory, we're going to initialize the CPU. Well, we're going to turn off shadow. We're going to initialize the CPU, any other initialization we need to do. And then we're going to drop into idle, which is just EI halt jump over and over and over again. In fact, we don't even need to do the EIs, just halt, jump idle, and so on. Because when we return from an interrupt, it should leave us interrupts enabled. What are the chances that somebody would mess that up? The chances are pretty good. Right. Belt and suspenders. So as we expand this cold boot, when we arrive at high memory, instead of this, we'll be doing things like read the first sector of the first track into memory and start it running. Or we may have even more. We may read the first 2 tracks into memory and start them running. We may initialize CPM. But this is a boot ROM. So I'm thinking that I'm going to put a to-do in here. Read first sector of first track of first diskette into memory at known address, then start the boot sector
Can we get the
running.
destroyer behind us while he's running that?
It will load and run more data from mass storage. So you call it read the boot record from mass storage. There we go. So this is all stuff that we can do now that we have this output port. We're not building the system yet, but we are trying to kind of define it. Okay, so we are an hour and a half into the session. I am going to take a small diversion at this point. In fact, let's put this back into Git as a new commit. Update boot ROM. Now that we have in and out, write a bit more boot code for a hypothetical system that has a control device, control register, an output port that can control the shadow facility, and an in port that gives some basic system status. Now I'm envisioning that this system state byte is not going to be really bits. It's going to be some sort of sequential number that says where we are in what we're doing. This will be something that will be kept up to date as you use the output to change the state of the simulation, to change the shadow or whatever. Input may read things back, like we may have in this register. If we're booting, if we're in this read this first sector, or if we're in the first stage boot or the second stage boot, or if we're in the system, or if we're in the idle loop, and so on. So there's a number of things we can do. I may also set up a series of ports that provides a high resolution clock, which increments based on the simulation tau counter. So we may have access to tau from within the simulation. It's always something that fascinates me, is having the system be able to benchmark itself at high precision. But this updates the boot ROM, so we've got bootrom.asm, stage the file. We've got the LST, boom, and we've got the hex file, which we can load. Notice how short this is. And the whole thing loads at FF8, OF F800, so it's F800 is the address part of this. commit, and push.
We have leather. And this is a
Okay, so we
really
implemented in and out. Oh, I need to actually have placed that in. I'll worry about that later. Often the documentation is going to lag for this. I still have all these to-dos about putting in comments, I know. Next step I'm going to do is ALU immediates. So add immediate, add with carry immediate, sub immediate, sub with borrow immediate, AN immediate, XRI immediate, and so on. And I'm going to put those back in the same file that does those operations. It will just have to use 2bops to get its operand. So I need to read over this really quick to remind myself how this works. We have state functions here for T4 and T2. Let me tease these apart a little bit. Come on. So we have the T4s, which are used here at M1 T4. Why did we only have T2s for a few things? RLC, RRC, RAL, and RAR all had T2s. The other ones didn't. I am going to have to read a lot more detail than I expected. Oh, these aren't the ones I want to be manipulating anyway. Okay, so getting rid of that. We want the one that has add, subtract, and all of that. Did that go in MISC? No, it did not go in MISC. Where did I put those? I thought I put those in ALU.
Remember, stack up, people.
Hold on. It's implemented. It really is. So we define all of these. Oh, right, because I didn't define them with MVI. It said 08 or whatever, or whatever, or whatever. So, no, I did not. This is in ALU. Oh, right, it's in here. Right, because it's all of this. All these M1, T1, and so on. Okay. So what I didn't do is I didn't go through and I did not read the entire file, which I should have done. So M1, T2 is here. And M1, T4 is here for all of these guys. So during M1, T4 of the normal add operation, what? Oh, right. Okay, bringing the PDF back up. Here's the trick. Where'd add go? Here. M1T4, we set up temp and act into these registers. Then we say return to M1. No, we don't. Why is this? So here. Oh, footnote 9. And footnote 9 is that special one that says the results of these arithmetic, logical, rotating instructions are not moved into the accumulator until T2 of the next instruction cycle, which is why the M1 T4 of these instructions says return to M1. So this M1 T4 sets up temp and ACT and says go to that one. So for the add immediate with data, ADI here, we do still put A in the ACT, but instead of pulling the M1 T1, or return M1, we now have a 2-bops which says get the instruction, and the 2-bops will feed it into temp, and that will feed back into the same T2 handler, which will occur in the M1 T2 there. So what we're doing is we are inserting this M2 cycle into the add to set TMP rather than this. So let's go back to the code. Get Kraken goes away. So LUT2 add, we want to take all of this stuff, add, and I want to do a duplicate of this, which is ADI. ACT and byte. So ADI does a lot more than that. Oh, no, T2 is going to do the same thing it did before. Hold on, isn't T2 a duplicate? T2 is just the same. It's the T1 that differs. So this is impl M1T4 for the opcodes. And for the opcodes that we were doing, it's all the same thing. Okay, so add, subtract, multiply, not multiply, add with carry, subtract with borrow, and so on, all did the same M1 T4 cycle. Where we're going to do something that's the same thing, but we'll only have one of them, and it's going to set up to set temp from the immediate. This is the M1 T4 cycle shared specify the 8 ALU ops when the second operand is the second byte of the operating opcode. Okay. And just to see how far I am from the real name, the real names look like static F8080 state and so on. So we want to now do a static F8080 state, I8080 state, ALU, IMMT4. Oh, just ALU IMMT4. So this is going to be shared. The next machine cycle collects. There, okay.
Dang, I was trying to get it.
I have a cat that needs to be held.
I believed in myself, and look what it got me.
What you want?
It got me dead.
He's got water and 2 kinds of food.
A Syrian has a bunch of soft serves. Most of the names are on a Syrian. I hope we get some.
Okay, Cat did not want to be held. She just wanted to lead me around the house a bit. So, LU immediate T4, this is going to head into CPU 2 bops T1. Okay. So now we need to hook this up. Oh, what are we doing here in the way of error messages so far?
Can I get some pre-spice?
Right.
Sorry, I was eating and drinking. Fucking myself, get me a pet.
So this guy isn't used yet. Now, he needs to be put into locations for all of these instructions. M1 T4 of op underscore that equal to I8080 state LU IMM T4. Okay. Now, in all of these cases, 2 bops T4 needs a M1T4, it needs an M2T3. Which means we need to go here, op underscore, we need to grab those three. And this is LU immediate, LU ADI T3. So we now have those 8 functions. Switching back to the PDF really quick. So ADI here, ADI. This is going to be here. This is really a T2 function, really. T3 to T2. How are we doing it? Doing M1, T2. So these all are going to be a common thing. Okay, so M1T4 is our, hold on, let's get down to it. Where did I put it? Here. So this guy is common to all the immediates. It simply says, this is a T4 cycle. We do nothing. We drop into 2 bops on the next one. Oh, we do put the ALU into accumulator temp. And this is the M2, M1T4, M2T3, shared by the 8 ALU ops. So M2T3, we need to grab the
I think the tornado got him.
data value and shove it in temp. And this is the last cycle.
Is Jahoon here? No? Wow, the people that suffers over there are not here. Okay. This makes it even funner.
So this says, once we've captured this, we're going to go on with the next M1T1. And in the process, we are going to dive in through the T2 mapping
Cindy and, oh, Bellamy coming in hot.
here.
Bellamy, are you a healer? Alright, so it's going to Simi in 3, 2, 1. Why are we putting a port? Also, these leggings were reserved, but they're not here, so guess what? Roll. These are super nice.
Okay, so I need to generate stuff that is a lot like these T2 ads.
We got the head to turn into
No, I
a
don't. I
really,
need to
really
use
nice
them.
neck piece.
Actually, I think I can use the T2 stuff from here to set it up as well. So we're going to grab this. For each operation, the M1T4 for all of the immediates is this guy,
When I get caught up, I'll need a few busts.
and the opcode for the immediates is, I've been coding behind the PDF again, haven't I? So ADI is C6. Turn off the PDF. So I'm not sure how much of that I coded behind. What we're doing is we're unifying things down. So we're going to step this through. The opcode here is going to step through. And you can do C0, followed by the opcode, followed by that. M1T4 is always this guy. And M2T3 is always this guy. And the M1T2 is the same one as this. Once we've gotten to this stage, we don't care whether it was immediate or not. These guys do not exist. So now, in theory, our immediates should now work. Let's scan it one more time by eye. We have our existing T4 and T2. The ones that lack T2s are because they do not require an ALU write back, a accumulator write back.
Oh, okay.
These instructions are the complete the instruction and write back to the ALU thing.
What I do is I target one on the outside and make sure my distract ring is hitting the outside of the group.
So here are our non-memory based things. Here's our memory based things. Really, at this point, this happens inside here. So let's do this. These are distinct operation codes, though. Hold on, hold on. PDF up. Oh, right, add immediate. The 6 is the memory. This is memory to do insert 2 bops for fetch from HL here. Thinking ahead to dealing with memory.
There's a very long timeout on that disk drive.
Just like here, where we're able to use the same closing, if we're coming from memory, we're going to use it here. So these guys will be just this. There. So we're not setting M1T4. These will continue to be unknown instructions. These guys are sharing the same T2 handler for the operation. Makes me wonder, does this guy really, what happens during that first thing, M1T4 of B, M1T4 changes based on the register. That's correct. Okay, so we're using the same thing to get from the register on all of those guys. So we're getting very close to having the next thing we do be the operations on M. Keep leaving the PDF up. Okay, so what I verified was that the M1T4s for the normal ALU operations were all sharing this where they could, and the difference between them is only which register is going into temp. We're good. And this means that operations on M are our next obvious thing to do, probably starting with the ALU operations. So let's set that up. So continuing with my desk check for the immediates. During M1T4, just to review, we're moving the A and ACT, heading off to 2 bops. 2 bops turns control back over to us where we signal the end of the machine cycle and stash the data in temp. And then we head down here to the T2s. And temp has one operand, ACT has the other. We do the T2, so this should be correct. So ALU test. This uses a whole bunch of prefab. This is not assembling a program and using it. This just does it directly off. So I think this is just a matter of adding in op ADI OX is something useful. So at the bottom of this guy, we're going to add an add immediate. So starting with T3, we're going to do a ADI and immediate something. So the A value was 87. And we need 18 there so that we get all the way through to the proper location. And the obvious thing to add to 87 would be 08. I don't think I have any of these guys setting the hef carry, do I? Nope, I do, right there. AC. Fine. But just for fun, let's have this do 0x0c. So the result should be 87 plus c is OX 9, 93. Right, right. And this is going to have, let's see, 93 is even parity. So the P bit is still on. It's going to have an alternate auxiliary carry, which is the 4 bit. So this could be 96. And it's still negative. So we did get an abort. So ADI is not actually being set up. Referring to the PDF really quickly, ADI is C6. So C6 should be right here. So that should be getting set up. So we are actually getting an FF, getting an FF instruction. Why would we be getting an FF instruction?
Yeah, just get the glue out. The helm of regrowth. Going to DE in 3, 2, 1. Ring token for warrior, shaman, mage, druid. Going to Grotesca with an 88. Shaman book.
So what is going on here? Let's take a look.
There's a road book. Going to the Bill Bank, thanks for that.
This is the add,
For the
LU add.
Rex, I'll be swapping over to my mage for the.
Now when we abort, we don't write stuff out very well. So we're going to go back to source support.c, and we're going to go down to the abort, and we're going to cut it out so we can get a plot.
Here, Bill.
And we are still aborting. That's because we're in state unyep. Of course we are. Shit. So what I'm going to do here,
At least it doesn't take as much mana as, say, like Priest Buffs. Alright, I'm switching to my mage, don't give my spot away.
okay, so the knops came up FF, FF, FF. Well, it came up FF and it didn't increment PC. So ADI somehow wound up dumping us off the end of the array. Not good. But we should at least have a plot of it. Yeah, you add. So we notice that weight went high here for a very long time. Which means I goofed up in source i8080 ALU.c. Somebody is supposed to be releasing weight and they're not. So it's that T3 cycle. Bingo, edge, low, CPU, arrow, weight. That may or may not be the real problem, but it is a problem. Okay, so there's the trace. M1T4, phase 137, M2T3, phase 13, got immediate data, which I didn't print. Got a C hex, that's correct. Ran the ADI, and we're before the NOPS, and we're getting IR is equal to FF here. What else am I missing here? DBN wasn't being lowered. Bingo, there's our culprit right there. Much better. So now we can take off these prints. So now that we've debugged that, and the error was in shared code, we should now be able to go through and do something similar to this in the other guys. So we have add ADI, sub, and the proper opcode for these is, let's get this correct, source I8080 ALU. Let's see. Nope, we need to go to Inc. So ADI is there. ACI. And then sub is, let's do them in order. Okay, so the final value is 8E. If I want to do something reasonable here, let's add 0C again. So 0C plus 8E is going to be 9, 1, 1. Oh, all right. C, B, and 9A, I think. So 0, 1, 0, carry
It's
the
in
1.
the door.
A, yeah.
I'm gonna tell y'all a funny story.
And 9A is
So,
even parity.
sometime
So
last week when I was farming for Felclough in Felwood, I got a pair of the edgies. And I kind of didn't know what to do with them because the auction house can be such a pain in the ass. And I just kind of stuck them in the bank. And so yesterday I was running around on my little level 20 mage on my Alliance side, and I saw somebody advertise in the trade channel want to buy Edgemasters. So I sent him a whisper.
Sorry, I'm just kind of puttering around here trying to insert the immediate tests. This is going to be a bit quiet. Okay, need a bit that hasn't been cleared yet. So we see it's C0. Let's set it up to clear the 8-0 bit. So this should come up with 4-0. Actually, it'd be interesting to include a test that ANIs it down all the way to 0. So let's put this instead of 4-0. Let's do it with 0F. I think that's going to be ZP. Yeah, 46. There we go.
So for the new
So yeah, more time spent writing and getting tests going than actually implementing the code. Not unusual. Okay, so CMP was derived from sub incompletely. Let's fix that.
I wouldn't waste your PI on Suze. I'm usually lagging behind picking up leads.
Okay, so that covers all of them. Obviously, the rest of these DAA and rotate and so on, these have no immediate variant.
It's going to Nuka.
Okay, so that finishes off the immediate instructions. Let's get into doc I-80. So the ALU immediates are done.
Rax, can you change the loop threshold?
I
so
think
that
I'm
I
done
don't have to
streaming.
worry-
Yep, okay. So that's enough for this session. I've got the in and out and ALU immediates done. I'm going to go off and think about what I want to do next. Probably do the operations on M next. Either that or the LDA STA stuff, or maybe I will dive right into stack operations. Don't know. I'm tempted to push stack operations down to the last. So I will see you for M operations addressed through HL in the next one. So until then, keep it small